Alright, let's do some physics here. Think about acceleration. This is a velocity versus time graph. It tells us how fast car A and car B were going at different times. Notably, this does not tell us anything about position. We can figure out displacements from this graph, like how far something went from where it started, but we don't know where they started. These starting values here, these are the starting velocities, right? So that's important to note that here. And here at this intersection point, that's where the two cars have the same velocity, but it does not mean that they're at the same place, right? I mean, I could be driving 70 miles an hour north on 81, and you could also be driving 70 miles an hour north on 81, but it doesn't mean that we're at the same place. It just means that we have the same velocity. So be careful about that. I think we see that intersection, we don't want to think that the cars are at the same place, but they are not. Describe the motion of car A in complete sentences. I'm going to go for one sentence that says it all. So car A here starts in negative direction because its starting velocity is negative 20, so it means it's going this way. Imagining that negative means left, like a number line. So it's in the negative direction at 20 meters per second. And then as it's getting closer to 0, it's going from negative 20 to having a velocity of 0. So where it has a velocity of 0, it's going from negative direction to positive direction, from negative direction to positive direction as it crosses over 0. So it's turning around there. Starts in negative direction at 20 meters per second, slows down, turns, or changes direction. I don't know if it's really turning around, maybe it's going into reverse, who knows. Changes direction at time, at time 10. And then after that point, its velocity is 0, and now I'm going into bigger positive numbers. So it speeds up in positive direction. Okay? I think a lot of physics students see this line going up, and they're like, oh, look, it's speeding up the whole time. But if you're going from negative numbers towards 0, that means you're actually slowing down from going in the negative direction. So negative 20, negative 10, and then to 0, and then into the positive numbers. Describe the motion of car B in complete sentences. So try to follow the same formula here. Starts in the positive direction, right? At 30 meters per second, looks like. And then it's also going toward 0. So looks like that happens. It gets to 0 velocity right here at time 30. So it starts in the positive direction at 30 meters per second, slows down, and then changes direction at time 30, and then now from time 30 it's getting into negative numbers, and those negative numbers are getting bigger, so that's speeding up in the negative direction. Then speeds up. I'm putting this in parentheses, these things, because if you turned around, then I guess if you were going in the negative direction and then you turned around, it's kind of obvious what direction you're going, but we can just be very careful to make sure we say everything. And then speeds up in the negative direction. What's the initial velocity of car A? Well, that's just its starting velocity, negative 20 meters per second. How do I know? This is the velocity at time 0, or in other words, the y-intercept. And then for car B, it starts at 30 meters per second. And this is the velocity, same reason, right? It's the y-intercept. You couldn't see that, could you? There we go. The acceleration of car A, the acceleration is the rate that the velocity is changing at. It's the slope of the velocity versus time graph. So for car A, what's the slope of this? Let's see if we can pick a couple easy points. Is it easy enough to see with the 10 here? I think it is. So I think rise over run, I'm going up 20 over 10. Up 20 over 10, so that's 2 meters per second squared. Show all work. So let me back up here, acceleration, change in velocity over change in time. In other words, it's the slope of this. So you can use any points you want there. I just used those two because I thought that would be easier, or easy. So change in velocity, I went from this one, from 0 minus negative 20. That's like VF minus VI, final minus initial, or V2 minus V1 if you want to think about it like the slope formula. T2 minus T1. And I shouldn't have written that right there because I needed to show all my work. That's what it says right here. So V2 minus V1. V2 is 0 minus negative 20. That's meters per second because those are velocities, over 10 minus 0 seconds. And that gives me 20 over 10, or in other words 2 meters per second. Maybe it's better to write it like this instead of the meters per second squared. I don't care which way you write it, but this makes it more obvious what it means. This means that for car A, for every 1 second that goes by, the velocity increases by 2 meters per second. For every 1 second that goes by, the velocity goes up by 2. How about the acceleration of car B? Same deal, looking for the slope. Looks like that is, if I use the same time interval, so the V2 is, that's my second one, would be 20 minus 30, and then 10 minus 0 for the times. That's velocities on the top, meters per second, and times on the bottom. So that's negative 10 over 10, or negative 1 meters per second So what's the meaning of this? For every 1 second that goes by, the velocity of car B decreases by 1 meter per second. All right. Keep that handy. Probably need to get back to that graph. Write a mathematical equation describing the velocity of car A as a function of time. In other words, just write the equation for this line, making sure you got the right units and the right names for the variables. Now, if you read this and you're like, I don't even know what that means, and you're like, oh, I'm just supposed to write the equation for that line, you need to pause the video right now. You got to make this an interactive process. Don't just kick back and watch me do physics. That's a waste of your time. So, and mine actually, because I already know how to do this. So let's make it work for both of us. So for car A, first of all, I'm thinking y equals mx plus b. I'm just going to write that up here, but I'm not going to use any of these letters. I'm thinking this. That's the form for writing the equation for a line. But on my y-axis, I've got velocity. That's the name of the variable. We call it v. That doesn't have units because it's the name of a variable. And then what's the slope? The slope for car A is this, with those units. These units are part of the slope. This whole thing, including the units, is the slope. 2 meters per second for every 1 second. I'm going to put the 1 down there. Now that's the slope. I have not yet written the horizontal axis variable. That's time. I call that t. Plus, that's the starting velocity. That's my intercept for car A is negative 20. Negative 20 what? Well, it's on the y-axis, negative 20 meters per second. I put a plus there, plus negative 20. You could just make that minus. Right? That is how you write the equation. That's y equals m, including the units, x plus b, including the units. Write a mathematical equation describing the velocity of car B, so same deal. Velocity equals, so these things are going to be the same, right? The v and the t, that's just like the y and the x are always there in all your equations for lines that you write in math class. So what was the slope of this one? It was negative 1 meters per second for every 1 second. And what was the starting velocity? It was 30. Right? Predict what the velocity of car A will be after 100 seconds. How would you do that? Because the graph only goes up to 80. I guess you could extend the graph, or you could kind of work it out with the slope. Or we've got an equation right here. All you need to do is plug the 100 into this. So the velocity at time 100 seconds is equal to, it's going to plug in the 100 right here. It's 2 meters per second every 1 second times 100 seconds, plugging it in there, minus 20 meters per second. So that's 2, look, the seconds cancel out, which is good. They get 200 meters per second minus 20 meters per second is 180 meters per second. Draw a qualitative, that means I don't have to include numbers, just got to get the relative sizes right. Motion map for car A. Well, car A, I'm going to go back to my description here. It starts in the negative direction, and don't care about the number, and then it slows down, and then it turns around and speeds up. So I'm just going to go for that basic idea. It starts in the negative direction. Remember, the arrows go halfway to the dots, and it slows down, and if the arrow is getting smaller, the dot gets closer, and I'll go one more in that direction, and then I'm going to drop down here because it's going to start going the other way and speeding up. Something like that. Why did I drop down here? Because if I didn't, the arrows would have gone crashing back into itself. The only reason I dropped that dot down is because I needed more room. From the graph, determine when the two cars have the same velocity. From the graph, it looks like they have the same velocity at, I don't know, times 17. I'm getting that from the graph, so that's approximate, I guess. How about if we do it algebraically? Well, I've got my equation, so you want to know when the velocities are the same? You set these equal to each other. My recommendation to you is when you go into algebra mode, you stop just to keep things a little bit cleaner, stop writing the units just for a minute. So the simplified, like with no units in it, the algebra-friendly version of this is 2t minus 20. And if we want to know when they have the same velocity, then I can set them equal to each other. And this is minus 1t, or just minus t plus 30. So doing some algebra, adding that over here, 3t, adding this over here is 50. So t is equal to 50 divided by 30, which I think is 16.7 if you round to the nearest tenth. So pretty close from just looking at the graph. Are the cars ever at the same position at the same time? And we talked about that a little bit at the beginning. Don't know. Justify answer. The no info about position is given. I don't know anything about position. I don't know where they start. I mean, one of them could be in Texas and the other one could be in Louisiana. For all I know, I guess those are right next to each other, those two states. That's a bad example. One is in California, one's in New York. I don't know. This just tells me information about how fast they're going. It doesn't say anything about where they are. All right, how about the average velocity of car A from 0 to 80? There's two ways to do this. You know what? I'm going to do 15 first, because I think that makes a little bit more sense. I'm going to do 15 and 17 before I do 14 and 16. So 15 is what's the displacement of car A. So car A, remember that if you, I'm going to draw in a little bit darker here where the axis is, where a position is, or sorry, where velocity is 0. Remember that if you've got a velocity time graph, that the area under velocity versus time is displacement. So for car A, I'm looking at this. The area under means wherever your line is. If you're looking at this saying, hey, McGrath, you said the area under and you're shading above. This really should say area under when people who are, in the game of doing this kind of math, when we say area under, we mean the area in between the line and the axis. It's always between the line and the axis. If you were tempted to do this, but I mean, the fact that this graph stopped at -60 is an arbitrary choice. This goes like down forever. So the area underneath this is just like a great chasm of nothingness. That can't be right. So we're going to go always from the line to the axis. And we want the displacement from, 0 to 80? 0 to 80, so that's the whole thing. So I've got this little triangle under here, and this gigantic triangle up here. Now here's the deal. When you're looking for displacement, displacement can be negative because you can end up further to the left than where you started. It would be a negative displacement. So this area here has to be, since it's underneath the axis, and we were only going in the negative direction, this is going to be a negative displacement here. So I have the area of this triangle. This is a 20 by 10 triangle, so 1/2 base times height is going to be 100 meters, and it's going to be negative. It's underneath. And then here I've got a base of going from 10 to 80. It's a base of 70 and a height of 140. So 1/2 base times height is going to give me, I think it's going to give me 4,900. Right? Isn't it 70 times 70? Yes, you say. So 1/2 base times height is going to give me 4,900, and that's all above. That's not a negative sign, that was from me underlining time before. So what's the displacement? Well, I got -100 and positive 4,900, so that is 4,800 meters. 4.8 kilometers if you want. What about unit conversions? All right, how about car B? Let's do that. I need a different color marker so I can make my triangles here. So here's the car B triangles. There's this one above, so that's going to be positive displacement. And then there's this one below. So for car B. I wish I had a little blue pen. This is a little bit overkill, but let's try that. Okay, so here, what's the area of this triangle? It's crosses here at 30, and it's 30 high and 30 wide. So 1/2 base times height is going to be 450. That's positive because it's above. And then here I've got 50 by 50. So that is negative, so 50 times 50 is 2,500, so half of that is negative 1,250 meters. So if I've got plus this and minus that, I think that's negative 800 total. You can use a calculator for all this, of course. All right. And last, so my work is on the front. You know I'm cool if you do something like that, right? Okay, so average velocity, 2 ways to do it. First of all, average velocity is displacement over time, by definition. So if you have the displacements, that is the easiest way to do it. What's the displacement for this one? It's 4,800 meters. What is the amount of time? It's from 0 to 80. So that's 4,800 over 80. That is 60 meters per second. And here, let's do the same thing with car B. We've got displacement of negative 800 over 80 seconds. So that's negative 10 meters per second. And that's it. So what's the other way? Well, if you've got a nice graph like this, the average velocity is whatever is exactly halfway in between the starting and the ending. So can you average those two numbers? For car A, we start at negative 20 and we end at 140. What's the average of those? So the other option would be just to average the initial and final velocity. In other words, it's the initial velocity plus the final velocity divided by 2. That's how you find the average of two numbers, right? Add them together, divide by 2. And if you do that for these, you're going to get, big surprise, the same answer, 60. You know what happens if you add together the starting velocity, 30, and the ending velocity, negative 50 of those? Let's see, 30 and negative 50. Guess what? It's the same answer. All right. There's a lot to think about and practice there. It's probably something you want to come back to at some point and practice doing those again.